Welcome to the Walton Pi. Today we're going to be talking about how to approximate integrals. So we might ask ourselves, why do we even need to approximate an integral? Why can't we just always evaluate the integral? Well, in some situations, we don't have an easy to write antiderivative of the function. So for example, the integral of e to the x squared, there is no easy way of writing that. In fact, we don't have a function that describes what that is beyond just saying the function that is the antiderivative of e to the x squared. We don't have a nice way of writing it. And so because of that, we don't really have a way to be able to evaluate this exactly. And so what we have to do in these situations is the only way for us to find what it's equal to is to actually approximate the integral, and we are going to now go through the process of how we're able to do that. Another function that you might see that seems like there should be a straightforward antiderivative, but there isn't, is the square root of 1 plus x cubed. We don't have a nice way of being able to write what the antiderivative of that is. So if you remember back to when we were introducing definite integrals, and if you don't, that video will be in the card, the way we defined a definite integral is to look at the limit of a sum of rectangles as the number of rectangles goes towards infinity. So what we could do is we could approximate a definite integral by using a finite sum rather than the infinite sum of rectangles. And so what we are going to do is we are going to talk about how we might be able to approximate it using a finite sum. So if we were to approximate it, sum of rectangles, we're able to choose how we determine the height of the rectangle. All we have to do is we have to have that height represent something inside the little subinterval. And so in this diagram we see 13 subintervals, each one with a different height, which matches the value of the function at a certain point. So if we were to break our domain up into n intervals, so in this diagram there are 13, if we then define the height of each rectangle as the value of the function at the right endpoint of the interval, we call that the right endpoint approximation. We're not getting super creative with their names, but they are very self-explanatory. So in this diagram, each of these subintervals, the right endpoint of the subinterval is the height of the rectangle. So you can see that each rectangle in the top right corner intersects the graph, and so that's how we were figuring out the heights of these different rectangles. What we could do is we could then write this down and be able to figure out what this would be. So the integral from a to b of f of x dx, so the area under this curve, can be approximated by a sum of n rectangles. And the way we are going to define it is it's going to be the sum from k equals 1 to n of f of x sub k times delta x, where we are able to then rewrite it like this. So this is just pulling out the sum into different terms, where delta x is b minus a over n, and x sub k is a plus k times delta x. So if we go back to the diagram, delta x is this distance here. It is the distance in one subinterval, and then x sub k, that is saying this is x sub 1, because this is after one interval. X sub 2 is after two intervals. This would be x sub 4 because it's after four intervals. And then we are just saying we are evaluating the function at that point. So that is saying, what is this value here? Or what is this value here for f of x sub k plus 2? And so that's how we would be able to go through and figure those out. What we could also do is we could do the same thing using a left endpoint approximation. So rather than using the right endpoints, we would use the left endpoints. And so this is almost the exact same, except instead of being f of x sub k, this is f of x sub k minus 1. Because instead of starting at our value is after one endpoint, it's after 0 intervals is where we start to evaluate. And so if we were to look at the sum from k equals 1 to n, f of x sub k minus 1, that is representing one term before, so we are starting at the 0 point. So that's how we would write the left endpoint approximation. So the left endpoint would be delta x times f of x0 plus f of x1 plus all the way up through f of x sub n plus 1. And again, just so that we have the definition of what delta x and x sub k are. Now, we don't only have to define this using the endpoints. We could also use the midpoints. And so what we could do is we could say, well, the midpoint approximation is the sum from k equals 1 to n of f of x sub k bar times delta x. Now x sub k bar is going to be the average of the two endpoints, and so we are just defining it as x sub k plus x sub k minus 1 all over 2. So this is just saying find the midpoint of each interval and then evaluate the function at the midpoint. Now, we don't only have to approximate it using rectangles. We could also approximate it using a trapezoid. And so this trapezoid approximation, this is a pretty good approximation for this curve. There's not a lot of places where there's a ton of overestimating or a ton of underestimating. So the trapezoid is often a good representation and often does better than those with rectangles, although this is not always the case. But in general, a general rule of thumb is the trapezoid approximation will probably be a better approximation. So the way we define the trapezoid approximation is it's the sum from k equals 1 to n of 1/2 f of x sub k minus 1 plus f of x sub k all times delta x. Now we might be asking ourselves, where is this equation even coming from? Well, f of x sub k minus 1, that would be like in this trapezoid here, that would be this height, and then f of x sub k would be this height. So if this is a trapezoid, these are our two bases of the trapezoid. And if we remember the definition of a trapezoid's area, it is 1/2 base 1 plus base 2 times the height. And in this case, the height is the delta x. And so this is just using the formula for the area of a trapezoid, and we are just putting it into a sum. So the trapezoid sum is, if we were to expand this all out, would become delta x over 2 times 1 f of x0 plus 2 f of x1 plus 2 f of x2, and so on all the way until we get a plus 2 f of x sub n minus 1 plus 1 f of x sub n. The reason that's coming from is if we are doing 1/2 of these two things, we have 1/2 of this one plus this one, but then for this trapezoid we also count this edge again. And so that is why we are going to have these 2's showing up inside the equation every time. And so again, just so that we have them, those are the definitions of delta x and x sub k. So let's go through an example now. Let's try and figure out what approximately the integral from 1 to 4 of 3x squared plus 2x minus 5 would be, where we are breaking this domain up into 6 pieces. Now, the reason I am doing this function as opposed to e to the x squared or something like that is we can actually evaluate what this integral is, so we can see that these approximations are actually going to be close to the actual answer. So, the first thing we need to know is we need to know what is delta x. So delta x is b minus a over n. Since n is 6, b is 4, and a is 1, we get 4 minus 1 over 6, which is 3/6 or 1/2. And then we can go through and calculate these different sums. So R6, so the right endpoint approximation, is the sum from k equals 1 to 6 of f of x sub k times delta x. So this is going to be 1/2 of f of 1.5 plus f of 2 plus f of 2.5, and so on until we get to an f of 4. Evaluating the function at each of those points will give us these values, and so the right approximation is 76.125. So that is going to be approximately what the integral from 1 to 4 of 3x squared plus 2x minus 5 would be. Next, we can go through and calculate the left endpoint approximation. So again, the only difference between the right endpoint and the left endpoint is where we are adding the terms. So the right endpoint starts at x sub 1 and goes through x sub n. The left endpoint will start at x sub 0 and go through x sub n minus 1. So here it's going to be 1/2 of f of 1 plus f of 1.5 all the way until we get to f of 3.5. So evaluating these is going to give us 50.625, which is different from the right endpoint. And so the odds are the true answer is somewhere in between those. We don't necessarily know where, but some of the other approximations might get us an even better guess. If we were to do the midpoint rule, this is going to be the sum from k equals 1 to 6 of f of x sub k bar times delta x. And if we need to remember what x sub k bar is, that's just the average of x sub k and x sub k minus 1. And so when we calculate these, this is going to be f of 1.25 plus f of 1.75, and so on. And when we evaluate this, this is going to give us 62.8125, which is between the 50 point something and the 70 point something that we had from our left and right endpoint approximations respectively. And so what we can also do is we can also then check the trapezoid. And so this is going to be our formula for the trapezoidal rule. And if we were to plug everything in, it becomes 1f of 1 plus 2f of 1.5 plus 2f of 2 and so on. And when we evaluate this, this is 63.375. So some of these approximations were closer to the true value because we can evaluate this and we find that the integral from 1 to 4 of 3x squared plus 2x minus 5 is 63. All of them were kind of close, but the right endpoint and the left endpoint were a lot farther off than the midpoint and the trapezoid rule. And so in general, the midpoint rule and the trapezoid rule are going to be the more accurate choices, although that is not always going to be the case. And if we were to increase the number of intervals, so maybe instead of doing R6, we were doing R100, so we calculated 100 subintervals, that would be an even better approximation. I hope this video was helpful in understanding these different approximations and how we can evaluate integrals using these approximations. And if it was, please like and subscribe so that I can continue to make these videos. Have a great rest of your day and good luck with your math.